All right, today we're going to talk about waves, springs, and oscillations. And it's a great unit. It's actually a pretty short unit for us, but we're going to start by defining what a wave is. So, what is a wave? And you think back, a lot of people can think about examples of waves, like maybe an earthquake wave, or the wave at a baseball game, or an ocean wave. But at the heart of every wave is a wave is a disturbance that transmits energy. So some vibration or disturbance, and the end result is a transfer of energy. And we can have sound waves, we can have earthquake wave. I put earthquake wave, but earthquake waves, plucked guitar string. And so just different things like that. So you have a disturbance that transmits energy. And maybe in math class you studied the shape of waves. And the reason I'm mentioning waves is because that shape of the waves, that's going to come back in the terms of sines and cosines in a little bit here. We can show where an object is, and the graph makes a shape you are familiar with. So what we're going to do, we're going to draw down this situation right here. It's a mass, and I meant to draw a block. It's not a great block. And it's a spring attached to a wall right there. And it's just hanging out at equilibrium. So draw this down. And then our goal is we're going to show where an object is, and the graph makes a shape that you're going to be familiar with. So this is just a mass and a spring hanging out in equilibrium. X equals 0 meters. Okay? And what we're going to do, so if you need to hit pause and draw that down, go ahead and hit pause and draw that down. But what we're going to do, we're going to apply a force, and we're going to stretch this mass out to a distance a away from the equilibrium position. Okay, so that's going to be our next drawing. So we're going to apply a force, and we're going to do that for a certain displacement. So you're putting work into the system. So you're going to do some work. You're going to stretch it out like that. And picture this. If you pull this object out and you do work, that spring mass system now has potential energy. And you might ask yourself the question, well, where did it get that energy from? It's because you did work. And so always remember that whatever work you did is equal and opposite to the change of potential energy. So in this case, it cost you some work, so now that object has that potential energy. In this case, it's not gravitational potential energy, it's the potential energy of a spring. Okay? And if you need to look up those formulas, the potential energy of a spring is 1/2 kx squared. So we have that, and then what you're going to do is you pull it back, and we all know if we pull back this mass in a spring, we all know what's going to happen. It wants to go back toward equilibrium, right? Because the force of a spring is negative kx. The negative just means it wants to restore itself back to equilibrium. It's a restoring force. You can picture what's going to happen. You pull it back, then it's going to go through the equilibrium position, but it's actually going to pass that, and it's going to go to a position, a distance a away on this side of the equilibrium position as well. Boom, right there. And I didn't label it, but it's going to crunch up like that. Then it's going to go back just like that to the equilibrium position. And then it's going to go back to A. Now, I'm assuming there's no friction, all right? Because we all know in real life there's something called damped oscillations where you get going less and less. So I made the note, if there were no friction, the block would go back and forth. It would oscillate forever. Oscillate's just a fancy word for going back and forth. If you want to sound smart, use the word oscillate. The child in the swing goes back and forth. The child in the swing oscillates back and forth. I mean, come on, which one sounds smarter, am I right? So I'll say, so we can graph the motion. And before I pull this down, your math and physics worlds, AP physics worlds, are about to collide. When you pull the mass back to position A right here, right? It's at A. That's what they call the amplitude, because it's never going to go farther than that, because you pull it back to a certain energy level, just like a roller coaster car. You can't climb a hill taller than the initial hill. It's the same thing here. You start at position A, and then it goes down to equilibrium, 0. So if you want to hit pause and draw this down, you can say the position's here, x in meters. I know it's a little weird to have position on the vertical axis and time's over here. And then you pull it and you release it. So we're charting the position of the mass in the spring after you release it. It goes toward equilibrium. Then it goes all the way down to negative A. So this is relative to equilibrium, 0. Then it goes to negative A. And then it goes back up to equilibrium, and it goes back. Now, one little note. The time it takes something to complete one cycle is called the period. Sometimes called the period of time, but usually people shorten it to, hey, what's the period? Kind of like in basketball, don't they have periods, or hockey, they have 3 periods. It's how much time, right? So they symbolize this special time with a capital T. The reason they use a capital T, because it's specific. It says, I started here. How long does it take to get back to here? Capital T says that's the period of time it takes to complete one wave cycle. So we started off talking about waves, and you're like, well, this wasn't a wave. Yeah, but when you graph its position versus time, that makes a wave, so that's how it ties in. So we have that going on, and just to look at it like, okay, it started at A, then it went to 0, then it went to negative A relative to that x equals 0, and then it went back to 0, went to A. That's exactly what we graphed right like that. And some people might be like, well, isn't it just like a sawtooth, like it looks like that? Well, no, because you can picture that it kind of gradually slows down to 0 there, then comes back. So I don't want to go into the exact part of that right there, but it does form what this is right here is a cosine wave. So it's kind of sweet. x versus t graph of a mass in a spring and I said horizontal mass in a spring is a cosine wave. And before we get into like the tougher math, I just want to review the parts of a wave because I'm going to reference these. And so before we get into the more mathy cosine sine stuff, let's just review the parts of a wave. And maybe you've never seen this before. And that's totally okay because we're going to go over it right now. So I had a lot of left-hand issues. You can see I've whited out some things. I was smearing. So I just drew a general wave right here. We're just going to label the parts of the wave. So I called part 1 and I labeled crest here and crest here. The wave crest, that's just the top of the wave. It's like the top of your head if you're thinking about it like that. So you want to stay over there. Okay, top of the wave, number 1, that's the crest. All right. Number 2, the opposite of a crest really is a trough. It's the bottom part of the wave. So I labeled the 2 troughs in the wave. So trough is the bottom part of the wave. And I am going quickly, so you probably have to hit pause and draw this down. And then a lot of times people get confused because they're like, how are crest and amplitude different? Here's how they're different. The crest is like the top of your head. The amplitude is the height of you. Okay, so just like the top of your head is different than your height, the crest is like, hey, that's the top part. The amplitude is the height right there. Okay, so we have amplitude is the height of the wave. And one thing, if you're ever in your car and you're turning up the volume, you're literally cranking up the amplitude. You're making the wave taller, and sometimes you crank it up too much, and your eardrum will have too great an amplitude, and that causes physical pain. So you're cranking up your volume, the amplitude there gets bigger, the amplitude of your eardrum is bigger, and that causes physical pain. So that's how the amplitude affects your life. And then we had the crest, the trough, we had the height of the wave, and we also have to talk about something called the width of the wave or the wavelength. And the wavelength is the width of the wave measured between identical parts. So it can be from the crest to the crest, like what's the width there, or from the trough to the trough. But it just has to be from some identical part of the wave to another identical part. And the symbol for wavelength, it's the Greek letter lambda. It's kind of fun. Don't get that confused. They use lambda in physics a couple other places. It's measured in meters though, because it is wavelength. All right, so that's the fundamental parts of a wave. And 2 vocab words we should add on 5 and 6. You're going to hear me use the word frequency. So what's the frequency? And your common sense physics brain says, oh, what's the frequency of going to the gym? That's just like saying, how often do I go to the gym, right? In terms of waves, what's the frequency of the wave? How many cycles can it make in a second? Okay, so how many cycles per second? And you'll see it on your radio dial in hertz or kilohertz or megahertz, but we use hertz, Hz, H-E-R-T-Z, they abbreviate Hz. So frequency is how often something happens, and I did not label that on the picture. You can picture a more frequent wave would be more crunched together and closer, and a less frequent wave would be spread out. And then number 6, we already kind of talked about the period of a wave. It's how many seconds it takes to complete one cycle. So how many seconds it takes to complete one cycle. And one little note, frequency and period, they're actually inverses of each other. Because you can picture if the period of a wave is really long, that means that it's not going to have a very high frequency, right? Because it'd be really stretched out. And if the period of a wave is really short, that means it completes a lot of cycles in a very short amount of time. And so the frequency would be higher. So it might be notable is that frequency goes up, the period of the wave goes down. If the frequency goes down, the period of the wave goes up. And there is a formula. I wouldn't worry about it. If you want to write it down, great. T equals 1 over F, the period of time equals 1 divided by the frequency. Or if you want to write it, frequency equals 1 divided by the period of time, you could do that. It's just rearranging the equation. That's a little wave introduction there because we're going to use those terms quite a bit. All right, we're going to go back to the shape of that wave. It was a cosine wave, right? And we know our general definition of the words, how to describe the wave. This is very cool because the position versus time of this mass in a spring system, I should have the word system there, is a cosine wave, cosine function, and we can work with this function. So here's the deal. I'm going to give you the general formula. When they write the general position of a mass on a spring or something oscillating back and forth, they write it as A, which is the amplitude, times the cosine, parenthesis, of omega t, plus this is the Greek letter phi, end parenthesis, and it is a vector. It's important to say that. Some people pronounce that phi. I remember looking that up once. I think the difference is masculine versus feminine. I don't know. I pronounce it phi. Let's just label some important terms here. That's where the mass in a spring is. So it's positioned. Just like when you're graphing, like, where is this thing? A is the amplitude or the maximum displacement. We drew that on our picture. If you want to go back and reference the picture, you can totally do that. Omega, I kind of made it look like a W. It is not. It's omega. It's something called angular frequency. And we're going to deal more with this. Write it down for now. But angular frequency is related to just straight up regular frequency. It's just omega equals 2 pi f. Don't stress about that now. It's not the main point of our lesson. I'm just having you put that in your notes. Plus phi, which is like your phase shift, because we all know we can have a cosine wave turn into a sine wave by shifting it by pi over 2, right? So that's just shifting it. So we have that. That's the general position function of something oscillating, and this is simple harmonic motion. We're going to talk about that more in a second. A couple notes. You know this from math class. The biggest a cosine function can ever be, the greatest value I ever have is 1, right? So if that were 1, you can say, oh, this is the biggest this can ever be is 1. Well, the maximum displacement then would be 1 times a, which is just a. So some things to note, and I had lefty issues again. X max is a, and that just makes sense with our picture from the beginning, right? And X min is negative a, but this model fits our picture. The reason it's going to get cool, and we're about to finish here, is if you ever have the position function, we can definitely derive the velocity function. How do we go from position land to velocity land? We have to take the derivative. So we're going to do that right now. And we have to take the derivative of the outside function with the inside function plugged in, and then times the whole thing by the derivative of the inside function. It's the chain rule. If you haven't done it in a while, it's fun. This is as tough as our derivatives get, so don't freak out if it's kind of tough. The derivative of cosine is negative sine. So I'm going to write that down. Negative sine, I put the negative there and put sine here. And then we say, okay, we took the derivative of that outside function, and we have the inside function plugged in, just omega t plus phi. We have that, and then we have to take it times by the derivative of the inside function. Well, we're taking the derivative with respect to time, so the derivative with respect to time of the inside function is just omega. So you can see I just times by the omega right there, and I just put it just like that. Phi is just a constant, so the derivative of that is 0. That's why phi doesn't make its way out to the front. And like, okay, that's pretty cool. We picked up a negative, which is kind of neat, and we picked up an omega, and then you're like, okay, that's dx dt, which is equal to velocity, but let's find the acceleration function. So we're going to take the derivative of this. The derivative of sine is cosine, and we have the inside function plugged in, and then we take that times the derivative of the inside function, which is omega again, so now omega times omega turns into omega squared. You're like, wow, that's pretty cool. Okay, I'm kind of seeing a pattern because it's periodic, right? Like I went cosine to sine, went back to cosine, just picked up a negative. Now, here is the thing. We just took the second derivative of position, or the first derivative of velocity, however you want to picture that. But and that is your acceleration of that mass going back and forth, just like that. So we have this, but then I underline this stuff in red because there's an a and there's a cosine of omega t. I'm like, whoa, there's a cosine of omega t plus phi, I should say, omega t plus phi. I'm like, that looks very familiar to my position function. So sometimes it's kind of cool. I'll say all the cool physics students do it this way. Instead of writing it kind of acceleration equals that, let's say, but a and that stuff right there, that's just your position function. So they'll actually rewrite it a equals negative omega squared, and then instead of writing the a and the cosine omega t plus phi, they say that's just my position function because it's cycled back. So that's how they write acceleration. Acceleration is equal to negative of your angular frequency squared times your position function. Your acceleration is proportional to your displacement, but it's in the opposite direction of your displacement. Okay, and we'll talk more about that. So that's a key way to write that. So note, a is not constant, so you cannot use kinematics. I've had students say, Laurent, can't we bring out the kinematics equations to figure out delta x equals 1/2 at squared plus v naught t? You can't do it. You know that when there's a force on a spring, F equals kx, and so the force depends on where you are. Well, if where you are is changing, that means the force is changing. If the net force is changing, that means the net acceleration is changing. If the net acceleration is changing, you cannot use kinematics. We're going to investigate this further in our next video, but if you can, at the end of this video, kind of be okay with, yeah, the position graph of a mass in a spring, it's going to oscillate back and forth. It makes a cosine function. And then we just said position, velocity, acceleration. That's a really great place to be right now. And yeah, we're going to rock on to something a little bit more complex, but it's cool. Thanks for watching.